we've talked about resistors in series, where the current must flow through each of them, and resistors in parallel, where the current gets a choice of pathways to go through. Many circuits are made up of a combination of those two things. So for example, let's imagine that we have a 12-volt power supply, and we have, what should we do? We'll have a 10-ohm resistor and a 5-ohm resistor, and up here we'll have a 20-ohm resistor. Okay, so we have the situation where as the current comes around, it gets to split in this piece in parallel, but then it's got to go through this thing. So this resistor and this block are in series. Okay, so this piece is a parallel piece, but that together with that are in series. So the current has to go through this bit and it has to go through that bit. Okay, so if we're trying to figure out what the total resistance is, it's going to be whatever this bit is plus this bit, because those two are in series. And to work out this bit, we're going to have to work out the resistance in parallel for that piece, and add it onto that piece in series to get the total resistance. So let's try and work out for a start what the total resistance for this circuit is. And then we're going to try and figure out what current goes through each piece, is the idea. So let's look at the resistance for the parallel piece. So that's just this piece here. So all I'm doing here is I'm working out what is the resistance for this piece. So the resistance for that piece, according to the formula, is 1/10 plus 1/5, which is, that's 2/10, and 1/10 is 3/10. And upside downify that, so that one is 10 over 3 ohms, so 3.33 ohms. I'll leave it as a fraction. Okay. So that blue piece is 10.33 ohms. And then the total resistance for the whole circuit is going to be the parallel piece plus the piece that's in series with. Well, what does that give us? That's 60 over 3, it's going to be 70 over 3 ohms. Yeah. Which you could work out as a decimal if you wanted to, but I'll leave it as a fraction at the moment. Okay, so we have a situation where we now know what the total resistance is. And once we know what the total resistance is, that lets us play with the total circuit. So I'm now going to apply Ohm's law. And whenever I apply Ohm's law, I want to have 2 points I'm thinking about between. So what current is going out of that one and into that one is going to be I, and it's whatever my full current is. It might split here, but it doesn't matter. It's just what leaves there and what comes back there. What's the voltage? Well, it's just your 12 volts. And what's the resistance between there and there? Well, it's the whole lot. It's the parallel bit plus the series bit, so that's 70 over 3. So now I can use Ohm's law between those two green dots to work out the current. So it's I is V divided by R, is 12 divided by 70 over 3, tip that upside down and multiply, 36/70ths of an amp. Again, we could work that as a decimal if we so wished. Okay, so the current that's flowing down this piece is 36/70ths of an amp. Right, and that's what's going to flow up through here as well. It's going to be that same amount. It's going to split, and then it's going to join back together. The only thing that we're really left with is trying to work out what's happening in either one of these two pieces here. We need to know what's going on there. So what we need to do here is think about looking at Ohm's law across just that piece. So I'm now going to do Ohm's law again, just across this piece here, and ask the question, what is the voltage between here and here? Okay? Because I know what the current is. The current is what I've just worked out. Yep, so that's that current coming through there. It's going to split up, but as it leaves that red dot, and arrives at that red dot, that's the current. I know what the resistance is between that red dot and that red dot, because I worked it out before, that's the 10 over 3. So I know the current and the resistance, so I can use Ohm's law to work out the voltage. So V equals I times R. I is 36 over 70, and the resistance for that piece I know is 10 over 3. So what does that leave me with? That cancels out to leave 12 over 7. Okay, so the voltage loss across this piece is 12 over 7, which again, if you wanted to, you could work out as a decimal. So I know between here and here what the voltage is. What I want is the current across one of these two resistors. So again, let's do Ohm's law again, between here and here. Okay, so I want Ohm's law across there to work out the current just for that piece. Remember, always Ohm's law between 2 points. So what's the resistance between here and here? Easy, 10 ohms. What's the current between there and there? Well, we don't know. All we know is that the current that arrives here is that bit, but it's going to split. So this piece is going to be a portion of it, and this piece is going to be the other portion of it. And we don't know quite how it's going to split yet. You could do some ratio work once you understand it, but let's assume we don't. So we don't know the current. What about the voltage? What's the voltage between here and here? Well, here's where you need the extra piece of information. As long as you are only moving along wires, the voltage doesn't change. It doesn't cost anything to move along wires. So if I know the voltage between here and here, as long as I only move along wires, I'll also know the voltage between here and here. The voltage at those red dots is exactly the same as the voltage at those green dots, because I've only moved across wires. If I went from here to here, it would change because I've gone across some resistance. But as long as I'm only along wires, it doesn't change the voltage. So the voltage here is exactly the same as the voltage here, which means I can now use Ohm's law across those two green dots. So the V equals IR, rearranged. I is V over R. The voltage across the green dots is exactly the same as the voltage across the red dots, and the resistance across the green dots is 10, so it tells us it's 10. Yep. So that's 12/70ths of a amp. Will go that way. And I could have done exactly the same for the 5 ohm resistor. Okay. Blue dots this time. But again, the voltage is exactly the same here. So the voltage on the green dots is the same as on the blue dots. So the voltage across resistors in parallel is the same for each resistor. And now again, I can do Ohm's law across the blue dots this time. I is V over R. The voltage across the red dots is 12/7 over 5, which is 12 over 35 amps. If we've done it properly, those two currents should add up to the total. So hopefully, if we've done it properly, let's label these things. So this is I, this one was I on the green dots, wasn't it? This is I green dots, and this is I blue dots. So let's add those two up. So I off the green dots, green, plus I off the blue dots, equals, what do we got? We've got 12 over 70 plus 12 over 35, which is 12, and that would be the same as 24, that's 36 over 70, which gets us back to the total current. So it has actually worked out okay. So we've been able to, with a little bit of mucking about and using Ohm's law always between 2 points, figure out everything about the circuit. So we now know what current flows in each bit, we know what the voltage is in each bit, we know what the resistance is in each bit. We could use our power equations to work out how much power comes out of each bit. Okay, so a couple of really important ideas there. Ohm's law, always between toe points. And that other idea, as long as you go along wires, the voltage doesn't change. A couple of really important ideas. And with those two ideas, you can work out everything you need to know about a circuit with a whole lot of combinations of things in it. Okay, so this is the level of circuits that's required for this course. It can have 3 resistors in any combination it likes. So that should be enough information to get you doing all the old exam questions on this topic. So have fun with some circuits.